Hello, welcome to Physics Explained, where we crack the code of nature. Let's dive into today's problem. So, here it is said a vertical glass tube of cross section S equal to 1 centimeter square contains a known amount of hydrogen. The upper end of the tube is closed, okay? The other end is opened and is immersed in a pan filled with mercury, okay? The tube and the pan are placed in a sealed chamber containing air at temperature T0 equal to 273 Kelvin, pressure P0 equal to 1.334 into 10 to the power 5 Pascal. Under these conditions, the height of the mercury column in the tube above the mercury level in the pan is H0 equals 0.7 meter. Okay, let's draw the diagram from this info. So here, this is a tube. This is the pan. Let's say I think this is not visible. Okay, this okay. This is mercury. This is the level of mercury. This uh, mercury is shining, right? So okay. Then it is said the area of cross section S is 1 centimeter square. There is some unknown amount of H2 gas. Okay. The other end is opened, is immersed in a pan filled with mercury. The tube and the pan are there is a chamber. This setup is inside a chamber. This chamber is sealed, okay. The temperature T0 equal to 273 Kelvin and P0 equal to 1.334 into 10 to the power 5 Pascal. This height H0 is given as 0.7 meter. Then it is said one of the walls of the chamber is a piston. Okay, let's say this is the wall. This is a piston. Okay, which expands the air isothermally. Okay, so this is scenario one, S1. I'm writing. So okay, um, hmm, which expands the air isothermally to a pressure P1, 8 into 10 to the power 4 Pascal. As a result, the height of the mercury column in the tube decreases to H1 0.4 meter. Then the chamber is heated up to a constant volume. Okay, so first write down the second scenario. Here is the our setup. We expanded isothermally. That means temperature is constant, right? So same. This is the pan. This is the sorry for my drawing. This is the pan. This is the tube, right? This is the chamber. Here is our mercury. Then there is H2 gas in the above. This height H1 is given as 0.4 meter. We expanded isothermally, so volume change, pressure will be also changed, temperature is constant. So P1 is given 8 into 10 to the power 4 Pascal. Then okay. Then this is scenario 2. Then the chamber is heated up to a constant volume to some temperature T2 until the mercury column rises to H2 0.5 meter. Okay. Then we heated, means we give thermal energy or heat at a constant volume. That is, this is an isocoric process. Isocoric process. After this, this is the pan, this is the tube, here it is mercury, uh, this is the chamber. Let this height, what, let H2 is, it is given 0.5 meter and the temperature is changed. This is given as T2. Okay, right? Then finally, the air in the chamber is expanded at constant pressure. That means isobaric process. And the mercury level in the tube settles at H3, 0.45 meter above the mercury level in the pan. Okay, this is scenario 3, right? Then we what? Hmm. Expanded at constant pressure, right? Expanded at constant pressure. Isobaric process. In the scenario is like S4. This is the tube, this is the pan, this is the chamber. This is mercury, mercury. Then finally, the air in the chamber is expanded at constant pressure. The mercury level in certain H3 is given as 0.45 meter. Okay. This height H3 is given 0.45 meter. Okay. Then what is it? Provided that system is in mechanical and thermal equilibrium during all the processes. Okay, mechanical equilibrium means the net force will be, what will be net force? That means pressure on this side will be pressure on this side, right? Thermal equilibrium means, suppose the hydrogen gas is a system S1 and the outside the air in the chamber is a system S2. When we expand or contract the piston, the temperature changes, the air's temperature changes. Means S2 system 2's temperature is changing. As it is in thermal equilibrium, S1 and S2 are in thermal equilibrium, it is given. So S1 will also have the same temperature as S2, right? This is what I want to say. Then we have to find mass of the hydrogen, intermediate temperature T2, and pressure P in the final state. Okay. We have to find mass of hydrogen, then T2, then T final. So the density of mercury at temperature T naught. Okay, the density is also varying, right? Of mercury is also varying. The density of mercury at temperature T naught is rho naught. Rho naught at temperature T naught is given as 1.36 into 10 to the power 4. 1.36 into 10 to the power 4 kg per meter cube. Then, okay, the coefficient expansion of mercury beta is given 1.84 into 10 to the power minus 4. 1.84 into 10 to the power minus 4 Kelvin inverse. And gas constant R is 8.314 joule mole Kelvin. The thermal expansion of the glass tube and variation of mercury level in the pattern are not considered. Okay. If delta T, there is a hint. 1 by 1 plus x, we can write as 1 minus x if x is very much less than 1. So let's try to solve. As we are interested in mass of H2, first we done the first part. So how can we find the mass of H2? Hmm, as it is, there is no mention of real gases, so I can consider H2 as ideal gas. Then I will the area is given. If I find somehow its height, then I can find the volume. I can find the pressure by mechanical equilibrium. So I can write PV equal to nRT. Thermal equilibrium, the temperature is same for a system S1 and S2. R is constant. So there I can find number of moles. Then I can find mass of H2, right? So let's try, let's write ideal gas equation in the four scenarios. So this is scenario one. There is a pan. This is the mercury level. This height H naught is given as 0.7 meter. This is H2 gas. This is the chamber. T naught is 273 Kelvin and pressure P naught is 1.334 into 10 to the power 5 Pascal. Okay. 1.334 into 10 to the power 5 Pascal. And the S is given as 1 cm square. So let the height of the tube is capital H. So I can write first, I'm writing the pressure term PV equal to nRT, right? Ideal gas equation. Ideal gas equation. So what will the pressure? Pressure will be pressure of H2 plus, as it is the mercury is in H naught height, its density is rho naught and there is Z acting downward. So pressure of H2, then pressure due to mercury I can write as rho naught G H naught is basically the outside pressure P naught. So pressure of H2 I can write P naught minus rho naught G H naught. Then volume. Volume is basically area into length. Area is given S. Length is basically H minus H naught. H minus H naught. Let the mass is M. So number of moles can be written as M by capital M, where M is the molar mass. Then is R and temperature T. Okay. The equation will be P naught minus rho naught G H naught into volume part. H minus H naught into S equals M by M number of moles R T naught. This is our equation 1. Okay. Then write for scenario 2. Scenario 2. We are isothermally expanding. This is our tube, this is the pan, this is the chamber. Here it's our mercury. This height h1 is given 0.4 meter. 0.4 meter. Then the pressure is 8 into 10 to the power 4 Pascal. P1 8 into 10 to the power 4 Pascal. Similarly, if I can, as it is isothermally expanding, so the temperature will be remain same. So if I write the ideal gas equation for hydrogen gas, then it will be similarly P1 minus rho naught. Why rho naught? Because the rho naught is dependent on temperature. Density is dependent on temperature. As the temperature is same, so the density will be same. Density of mercury will be same. So rho naught G H1 height is changed. Capital H. Tube's length is constant, right? There is written not to consider any expansion of glass tube. So H minus H naught H1 into S equals M by M as mass is constant. M by M R T loop. This is equation. So here you can see that. So okay, okay, we can solve. P naught is given, rho naught is given, G we know, H naught is also given, H naught given, S is given, capital M we know, R is given, T naught is given. So here is variable H and M. P1 is given, rho naught is given, G we know, H1 is given, capital which you don't know, H1 is given, S is given, capital M we know, R is given, T naught is given. Here is also H and M variable. We solve these two equations, then we get height of tube and mass of hydrogen present. Our first intention is to find the mass, right? So let's solve the equation. Here you can say if I directly divide this equation, the RHS part will be 1 and left hand side will be this. So if I divide P naught minus rho naught G H naught H minus H naught into S is basically P1 minus rho naught G H1 H minus H1 into S. S and it cancels. So P naught is given as 1.334 into 10 to the power 5 minus rho naught is the value of rho naught. Rho naught 1.36 into 10 to the power 4. Okay. 1.36 into 10 to the power 4 into 10 value G into H naught. H naught is 0.7 meter. 0.7 into H minus 0.7 P1 is 8 into 10 to the power 4 minus density is same 1.36 into 10 to the power 4 into 10. Height is 0.4. H minus H1 0.4. Okay. So the calculation is pretty lengthy. Oh, don't judge me, but I'm going to use calculator. Who in the world will calculate this? Pretty much time taking, right? So 1.334 into 10 to the power 5, then minus sign 1.36 into 10 to the power 5 into 0.7. This value comes as 38200. H minus 0.7, then right hand side 8 into 10 to the power 4 minus 1.36 into 10 to the power 4 into 10 into 0.4. This value comes 25,600. 25,600 H minus 0.4. Then use 38200 H minus 38200 into 0.7. This is 26740, then 25600 H minus 25600 into 0.4. 10240. Then is 38200 minus 25600 H is 26740 minus 10240. So 38200 minus 25600. This is 12600 H is equal to 26740 minus 10240. This is 16500. Here H I get 16500 divided by 12600. We are getting 1.31 meters. This is the height of the tube. If we put in any of the equation, we can find the mass. So let's put in the equation 1. Put in value of H in equation 1. So this part we have calculated here. This is sorry. This is 38200, right? 38200. Height is 1.31 minus 0.7 into there is a S term in equation 1. S, sorry, in equation 1. S is 1 cm square. 1 cm square is 10 to the power 4. 10 to the power minus 4 meters square equals M by capital M, we know 2 gram per mole. Then there is molar mass is 2 gram, right? So then R is 8.314, temperature is 273. If we calculate this, mass comes at 38200. 1.31 minus 0.7, this is 0.61 into 10 to the power minus 4 into 2 divided by 8.314 into 273. Calculate 38200 into 0.61 into 10 to the power minus 4 into 2 divided by 8.314 divided by 273. This comes as 2.05 into 10 to the power minus 3 gram. The battery is low. That's gram. Is weight I'm charging. Okay. Now I think it's okay. We got the mass of hydrogen, right? 2.05 into 10 to the power minus 3. It is our first one. This is the answer of it. Then it is said to find the temperature T2. Temperature T2 is in scenario 3, right? Okay. So this is scenario 3. This is our tube. This is our pan. This is our chamber. I think at constant volume. Heated in constant volume. That means this is an isochloric process. Here is our mercury. This height is H2. H2 is H2. Okay. H2 is 0.5 meter, right? This is 0.5 meter. Its temperature is T2. As it is an isochloric process, so volume, ratio of volume and sorry, ratio of pressure and temperature will be constant as it is an isochloric process, right? So suppose the previous one, system 2, has pressure P1 and temperature T0. System 3, let pressure is P2, temperature is T2. So I can write P1 by T0 equals P2 by T2. Here I can write P2 is basically P1 T2 divided by T0, right? So let's write down the ideal gas equation for hydrogen. So its pressure is P2, we have assumed. So P2 minus uh, here temperature is changed. That's why density of mercury will be changed. How can you see that? We know for let beta is the volume metric coefficient of thermal expansion. Thermal expansion. So volume final will be volume initial 1 plus beta delta T. So we want to find rho. Rho is basically density is basically mass per volume. So Rho initial as mass is constant. Mass by volume initial. Rho final is mass by volume final. I can write as volume final. Rho final is mass by volume final is V initial 1 plus beta delta T. This mass by volume initial is basically rho initial. So rho final is equal rho initial at 1 plus beta delta T. Here beta delta is very much less than 1 because beta is in the order of 10 to the power minus 4, right? So we can use that approximation. So rho final is rho initial 1 minus beta delta t. So if you write the ideal gas equation for hydrogen, P2 rho let that's rho not right. So let it is rho 1. Rho 1 G H2 H minus H2 into S equals M by M R T2. So we want to find T2, right? So if P2 in terms of P2 is P1 T2 by T naught minus rho 1 is basically rho naught 1 minus beta change in temperature and H minus H2 into S M by M R T2. This beta delta T is beta into T2 minus T. Okay, so P1 P1's value is 8 into 10 to the power 4 Pascal, right? So 8 into 10 to the power 4 into T2 divided T naught is 273 minus rho naught is I guess 1.36 into 10 to the power 4. What's that? Rho naught is 1.36 into 10 to the power 4. Yeah. Then G is I G into H2. Rho naught into 1 minus beta is the value beta. Beta 1.84 into 10 to the power minus. Wow. Okay. 1.84 into 10 to the power minus 4 delta T is T2 minus T naught into G into H into H2. H2 is given 0.5 into H minus H2. H is 1.31 minus H2 is 0.5 into S is 10 to the power minus 4 M on 2.05 into 10 to the power minus 2.05 divided by 10 to the power minus into 10 to the power minus 3 divided by the 2 capital M is 2 R is 8.314 and there is 2. Let's use the calculator. 8 into 10 to the power 4 divided by 273. This is 293.04 T2 minus 1.36 into 10 to the power 4 into the power 4 into 10 into 0.5. So this is 68000 1.36 into 10 to the power 4 into 10 into 0.5 into 1.84 into 10 to the power minus 4. This is 12.5 into 12.512 T2 minus into 273. This is 3415.776 into there is 1.31 minus 0.5. This is I can calculate. 0.81 into 10 to the minus 2.05 into 10 to the power minus 3 into 8.314 divided by 2 is 8.52 into 10 to the power minus 3. That is all. Yeah, there is a term T2 in the right hand side. So, so much term there. 293, okay, 0.04 plus 12.512. So this is 305.552 minus, sorry, there is a T2, T2 minus 68000, 3415.776. This is 71415.776 into this guy 0.81 into 10 to the power minus 4 and equal to 8.52 into 10 to the power minus 3 T2. 305.552 into 0.81 into 10 to the power minus 4. This is 0.0247 T2 minus 7141.5.776 into 0.81 into 10 to the power minus 4. It's basically 5.78. This is 8.52 into 10 to the power minus 3 T2. So here we can 0.0247 minus 8.52 into 10 to the power minus 3, basically 0.01618 T2 equals 5.78. T2 is basically 5.78 divided by 0.01618. Temperature, you get 357.23 Kelvin. Then our final intention is to find T2. I think sorry, the it is said to find the P final. So P final means the pressure in scenario 4, but as from scenario 3 to scenario 4, it is expanded at constant pressure. That means it is an isobaric process. So the pressure in scenario 3 is equal to pressure in scenario 4. So there is no need to write the ideal equation in scenario 4. We can write for find any other parameters like volume or any other things like temperature. So I can write the pressure in scenario 3 is the final temperature, right? As it is in isobaric process. So pressure in scenario 3 we have written P2 equal to P1 T2 by T naught. So pressure final is basically P1 T2 by T naught. P1 is I guess 8 into 10 to the power 4. T2 is 357.23. T naught is 273, right? So yes, the pressure is 8 into 10 to the power 4, right? So if we calculate this, 8 into 10 to the power 4 into 357.23 divided by 273. This can 1 0.4682.7839. I can write it 1.046827839 into 10 to the power 5 Pascal. So I approach 1.05 into 10 to the power 5 Pascal. This is the answer. So the data is such that the calculation is very many. The concept is, I think, it's quite easy to handle. I hope you enjoyed this video. If you have any queries, write it down on the comment section. Let's meet in the next video. Thank you.